Flexible filaments used to be some of the most challenging materials to print with, but thanks to advancements in modern 3D printers, most can now be printed with surprisingly little effort. As printers have improved, we've seen some fascinating new flexible materials emerge. We've looked at PIBA for its incredible energy return, foaming TPUs for making lightweight parts, and Moreflex, a footwear-focused filament that gets softer after it's been printed. But there's one material I've been hearing about for some time now that I've had a hard time wrapping my head around. Glass fiber TPU. The idea of reinforcing a flexible filament with glass fiber just seems completely backwards. That opportunity finally came when QIDI sent over a spool of their glass-filled TPU along with their new printer, the Plus5, giving me the chance to finally put it through some testing. In this video, we'll dive into glass-filled TPU, what the material is, its properties, what's required to print with it, and of course, we'll do some printing. So with all that being said, and without further ado, let's get right into today's video. Before we dive into this particular filament, let's quickly talk about TPU. TPU, or thermoplastic polyurethane, is one of the most versatile 3D printing filaments out there. Its flexibility, impact resistance, and abrasion resistance make it perfect for everything from phone cases and gaskets to vibration dampeners, protective bumpers, and even things like RC tires. It also tends to have fantastic inner layer adhesion, making parts that are incredibly tough and difficult to pull apart at their layer lines. Of course, TPU isn't a one-size-fits-all. It comes in a wide range of different shore hardnesses, and adjusting things like wall count, infill, and sometimes even temperature can directly impact how flexible or rigid the finished part is. But adding glass fiber to the TPU isn't simply just another way to make the material more rigid. And in the case of QIDI's glass-filled TPU, it is made up of 15% chopped glass fiber. That reinforcement can help improve characteristics like dimensional stability, wear resistance, and heat resistance, while still retaining the impact resistance and toughness that makes TPU so useful in the first place. With any filament we cover, I like to start by taking a look at the manufacturer's TDS to get a general idea of its mechanical and thermal properties. I'll have those on screen as well as a link in the description if you want to take a closer look for yourself, but there are a couple of things that stood out to me that I want to make sure I highlight. The first thing that stood out to me is the VICAT softening temperature, which is listed at 157.3 Celsius. I compared this to a handful of other more standard non-filled TPUs and found this to be substantially higher by approximately 50 to 60%. But what piqued my interest was that QIDI used the VICAT softening temperature at all. Most of the filaments we've covered on this channel, in their TDS, it displays the HDT, or heat deflection temperature, as the measurement for a material's heat resistance. After looking into it more, I discovered that most manufacturers are using the VICAT softening temperature in their TDS when we're talking about a TPU or another flexible filament. And there's a good reason for that. HDT measures how much a material deforms under a load, which isn't exactly useful for a material that's already flexible to begin with. VICAT instead measures softening by pressing a standardized needle into the material as it's heated, with the reported temperature being the point at which it penetrates 1 millimeter. When comparing this material to QIDI's own 95A TPU high flow, one of the most obvious differences between the two is those materials' shore hardnesses. Like the name implies, QIDI's 95A TPU has a shore hardness rating of 95A, while the glass-filled TPU has a rating of 67D. Because the A and D scale overlap but aren't directly interchangeable, you can't simply count it as an increase in percentage, but 67D puts the glass-filled TPU firmly in the semi-rigid zone. We can get an even better idea of how differently these two materials behave by looking at their elongation at break. The 95A TPU can elongate at around 471% before breaking, compared to the TPU-GF, which reaches just under 75%. So while the glass-filled version can still undergo a fair amount of deformation, it is substantially harder than your typical 95A TPU. Now let's go over exactly what's required to print with this material. The good news is that if you've printed with a TPU and you've printed with an abrasive material, chances are you've got everything you need to print with the glass-filled TPU. Starting with the hot end. QIDI recommends a nozzle or printing temperature between 240 and 270 Celsius. So while this is a bit warmer than most TPUs, any all-metal hot end will have no problem reaching those temperatures. For the extruder, QIDI recommends direct drive, especially if you're going to try to push your printing speeds. With this being a much harder TPU, I wouldn't anticipate you'd have much issue using a Bowden setup to print with it, but I would recommend starting at slower speeds and then ramping up once you've seen that you're getting consistent extrusion. For the build plate, they recommend a temperature between 40 and 60 Celsius, and they have glass, PEI, or PC film listed as the approved or recommended surface materials. For all my printing, I use powder-coated PEI, and to play it safe and prevent any sort of accidental damage, that's my recommendation over a glass or any sort of a surface sheet. For part cooling, they recommend between 20 to 50%, although that is something that you may want to adjust depending on what you're printing and what the specific application of that part is. QIDI's own testing shows a higher Z direction tear strength on the part printed with no cooling as compared to the one printed with 50% cooling. So if you're trying to maximize and get the absolute best interlayer adhesion, you may want to consider lowering or even turning off the part cooling. And finally, we have the nozzle. QIDI recommends a minimum orifice of 0.4, and because this is containing 50% chopped glass fiber, you will need to make sure you have a wear-resistant nozzle. Today's video is sponsored by PCBWay. Here on the channel, we do a lot of 3D printing, and while 3D printing is absolutely near and dear to me, sometimes a project calls for a different manufacturing process. PCBWay offers a huge range of manufacturing services, including custom PCBs, CNC machining, sheet metal fabrication, injection molding, and even several different 3D printing technologies. For PCBs, you can upload your Gerber file directly to their website, configure your boards, and even have PCBWay handle assembly if you don't want to solder everything yourself. And for mechanical parts, their CNC machining service supports a wide range of metals and plastics, making it possible to have parts manufactured that might not be practical to make at home. So whether you're working on an electronics project or just want to explore a different manufacturing process beyond what you can do at your own shop, you can check out PCBWay using the link in the description. A huge thanks to PCBWay for sponsoring today's video. And now, back to our glass-filled TPU. The Plus5 checks all the boxes as far as requirements go for this material, which is a good thing because that's what I'll be using for the testing. Since I'm using this printer, I jumped into QIDI Studio and saw that they already had a profile for this particular filament. So of course I had to dive in and see what sort of default settings they were running. The hot end temperature was set to 240 Celsius, which was at the bottom of their recommended range, and the bed was set to 35 Celsius, which is actually lower than the recommended range that they had listed in their TDS. The max volumetric speed was set to 6 cubic millimeters a second, so fairly conservative, and while they had the auxiliary fan set to off, the part cooling fan other than the first layer was set to 100% cooling. This was a little surprising considering their recommended range was between 20 to 50%, and their own test showed that the parts printed had a higher Z tear strength with the no cooling at all versus the one with 50% cooling. Before printing, there is one other thing worth mentioning, and that's moisture. Like other TPUs, TPU glass fiber is hygroscopic, meaning that it absorbs moisture from the air around it. QIDI recommends drying this filament between 70 to 80 Celsius for 4 to 6 hours if it's absorbed moisture. In my case, because I took this out of a brand new vacuum sealed bag with some desiccant, I threw it in the dryer for a little bit over an hour and then proceeded to print with it. As for the printing, I've been building the Cassadio Unimog massive RC truck over on the Modbot Army channel using the LDO kit, and really wanted to find some parts for that build that would benefit from using this glass-filled TPU. I ended up deciding on the fenders, front bumper, side mirrors, and mud flaps, starting with the fenders. So I loaded up the STL files, adjusted the strength and layer height settings to match with the recommendations in the project's printing matrix, and fired off the first parts to be printed. Given the almost non-existent bed temperature from the default profile, and considering glass-filled TPU is quite different than anything I'd ever printed before, I cautiously watched as the first couple of layers of material were laid down. But it didn't take long for my concerns to turn into excitement as I watched gorgeous, super clean layers stack on top of each other as these fenders began to take shape. Like most filaments that contain a chopped glass or a chopped carbon fiber, the layer lines are almost non-existent, and instead you get this really nice sort of uniform texture across the entire surface of the parts. When the part's finished, there was really no need to wait for the bed to cool down because, well, it was practically cooled to begin with. I found that with the powder-coated PEI, there was a little bit of a bite, but with just a little bit of flexing, they came right off. Definitely easier than I'm used to with a non-filled TPU filament. The fenders were printed at a 5% gyroid infill, and that combined with the thin geometry of these parts meant that I could relatively easily twist them back and forth. Even printing at the lower end of the recommended temperature range, I didn't notice any sort of delamination or just cracking sounds as I twisted this back and forth. The part feels solid. It's been quite a few years since I've printed with a non-filled nylon or PA material. I don't actually think I have any in my library of filaments, but something about this, with its sort of stiffness but still having a bit of give to it, reminds me of what I remember when I printed with some nylons many years ago. The bumper was printed with 10% gyroid infill and is a much bulkier part, so outside of the little cavities that I can kind of squeeze from the side, it is substantially more rigid. The sides of the front bumper have some pretty decent overhangs for the pockets or cavities that the various headlights will go into, and they turned out really clean, and the part had minimal to no stringing at all. These parts feel like they are going to be perfect for the RC build, and I'm curious to see how they hold up to the inevitable impact once I actually get the project and the truck up and running. Since all of these parts had been printed on QIDI's printer with their own default profile, I wanted to test out at least one print on a different machine. So I jumped into Flash Studio and put together a profile closely resembling the one that QIDI had in their slicer for the Creator 5 Pro. I then loaded the glass-filled TPU into one of the tools and PLA into another one. In the past handful of months, I've printed this airless tennis ball in both 95A TPU as well as PEBA or PEBA, so it only felt right that I also made one in the glass-filled TPU. I loaded in the file, set the supports to use the PLA with a 0 distance gap, and sent it off. The print completed without any issues, and it was by far the easiest time I've ever had removing a PLA support from any of the TPUs or flexibles that I've used PLA supports with. Of course, I had to see how it bounced. So I had my assistant take 2 of the tennis balls and drop them from as close to the same height as possible so that we could compare them. Given the added rigidity caused by that glass fiber, I was expecting this to bounce really well, but it just beat out the 95A TPU by a little bit, and there was no competition against the PEBA. It is clearly still the undefeated winner. So what are my thoughts on glass-filled TPU based on my time with it so far? Well, when I first saw this filament, I had to do a bit of a double take. At this point, I've seen chopped glass and chopped carbon combined with just about every material out there, but I can't say that I ever really expected to see it combined with a TPU. I think my biggest question when I first saw it was, why? But after learning more about it and finally getting a chance to print with it, I think this is by far one of the more underrated filaments that I've tested, and I anticipate its popularity is only going to grow as more people learn about this filament. It prints great, looks incredible, and while it's much stiffer than any other TPU I've printed, it still retains enough of that flexibility and toughness to make it useful in situations where a completely rigid material may not be ideal. Add in the improved temperature resistance, abrasion resistance, and dimensional stability, and I think I finally understand why you may want to add glass fibers to TPU in the first place. For functional parts like these pieces for the RC build, I think that combination makes a ton of sense. And that's been TPU glass fiber or glass-filled TPU. I know I've been using them interchangeably. I hope that you enjoyed this video, that you have a better understanding of what this material is and whether it makes sense and is worth checking out for an upcoming project. If you have any questions, let me know in the comments and I will do my best to answer. As always, if I don't know the answer to your questions, I have no problem reaching out directly to QIDI to try to get those answers for you. On that note, don't forget to like and subscribe for more great videos. We make a video just about every other week, so there's always fresh content coming your way. If you want to support the channel further, I'll have links in the description over to our Patreon, where there are some really awesome rewards. Huge thank you to all of our existing Patreon supporters. I appreciate each and every one of you for allowing me to come back every single week and spend more time doing what I love, which is making content for you all to enjoy. On that note, this has been Daniel from ModBot. I look forward to seeing you guys in my next video. Peace, guys!